Okay, so first, let me just thank the members of my group and collaborators who contributed to what I will talk about. So this is the outline of the talk. So it will consist of two parts. And so the main message of the first part of the talk is going to be that we should think of topological semimetals as really a new way a metallic phase can be realized. Okay? And so I'll try to place the topological semimetals into a broader picture of metallic phase of matter in general, and using this idea of anomalies of emergent symmetries and generalized Lachenger's theorem. Okay? And then in the second part of the talk will be more traditional, so I'll just talk about basically some transport properties of topological semimetals, some of which have been observed already. Okay, so when we let's start with ordinary metals, right? So you know that from ordinary solid state physics, undergrad solid state physics, basically that what determines whether a given material is a metal or an insulator is a single parameter, basically the number of electrons per unit cell per spin, and I will call this filling, okay, or nu, okay. So basically, when that number is fractional, so then we have, then the material is a metal, and so we have a Fermi surface of gapless excitations in the Brillouin zone, and the volume enclosed by that Fermi surface in the Brillouin zone divided by the total volume of the Brillouin zone is equal to the fractional part of that parameter of the filling. Okay. So this statement is known as Lachenger's theorem. And so whenever, again, that number is fractional, the material is a metal. So when that number is integer, then it's an insulator. It can also be an accidental semi-metal where, conduction and valence bands overlap. But that, in principle, that overlap can be removed without really altering the symmetry of the material. So I will still call it an insulator. And so from this viewpoint, we can think of a metal as an intermediate phase between two insulators that correspond to neighboring integer values of this filling parameter, right? And so any non-integer value of nu, again, between the neighboring two integers, requires that we have gapless excitations in the form of a Fermi surface and therefore a metal. And so what we've realized in the last decade or so is that there is a new way in which a metallic phase may arise. So these are these topological semimetals. So these are bulk three-dimensional semimetals which arise at integer values of the filling parameter that would normally correspond to an insulator. But so they arise as intermediate phases between insulators that correspond to the same integer values of nu, but have different electronic structure topology. Okay, so for example, the simplest topological semimetal, the magnetic wire semimetal, we can think of this as an intermediate phase between an ordinary insulator in 3 dimensions and an integer quantum Hall insulator, okay, which is a stack of 2-dimensional quantum Hall insulators. A non-magnetic wire semimetal can be thought of as an intermediate phase between, again, an ordinary insulator and 3-dimensional weak quantum spin Hall insulator, or weak time reversal invariant topological insulator. A type 1 Dirac semimetal, which has a pair of Dirac points on the rotation axis, may be thought of as an intermediate phase between ordinary insulator and a topological crystalline insulator protected by rotational symmetry. Another line semimetal, another example of topological semimetal. That's an intermediate phase between ordinary insulator and again topological crystalline insulator that's protected by mirror symmetry. Okay, so they're all again intermediate phases between ordinary insulator and some weak topological insulator in 3D. And so, again, the main message of this first part of my talk is going to be that both ordinary metals And topological semimetals may be characterized by topological response, which takes the form of what's called a mixed anomaly involving symmetries characterizing these phases, such as charge conservation, translation, rotation, etc. And I will explain what that anomaly means. And so we should think of this as basically a generalization of the Lattinger's theorem that we know from ordinary metals to this case. Okay? Okay, so let me start from the simplest example. I'll explain what this means on the simplest example. So let's just take a spinless, for simplicity, one-dimensional metal. Okay? So in this case, this is a typical band structure of a one-dimensional metal, right? So I have two Fermi points at Kf and minus Kf. Okay? And so the Lattinger's theorem is telling me that the ratio of the length of this interval between the two Fermi points, 2Kf, divided by the volume of the brilliant zone, which is just the size of the reciprocal lattice vector, 2 pi over A, is equal to this Lattinger parameter nu, right? It's a fraction that tells me how many electrons per unit cell I have. Okay? And so what I want to do now, well, this statement, of course, is trivial when you think about non-interacting electrons. The non-trivial thing is that this actually transcends non-interacting electrons, and it's true even with interactions, with disorder, and so on. And so what I want to do now is connect the left-hand side of this and the right-hand side without referring to non-interacting electrons. Okay? Okay, so, so I can express the right-hand side. The right-hand side just tells me that I have a charge density of nu over A, right, in this metal, and I can express this in terms of an imaginary time action that looks like this. So this is just the coupling of my charge density rho, which is nu over A, to the time component of the electromagnetic gauge potential, right, to the electrostatic potential. And I can obtain that by differentiating this action with respect to the electrostatic potential, with respect to A0, right? Now, so there is nothing topological here, of course. So the charge density explicitly depends on the length scale on this lattice constant. But on the other hand, you can notice the following thing, that if I differentiate this action twice, if I differentiate it first with respect to A0 as before, and then formally with respect to 1 over A, then I just get this number. Okay? And so even though this number is not an integer, as I will argue, you can still view this as kind of an index, a topological index that characterizes my metal, again, even though it's not an integer. Okay? Now, what this formula suggests is that I might be able to think of 1 over A as another gauge field. Okay? So this sounds crazy, but it's not. Or, I mean, I can also state this less provocatively. I can just say that the real useful information is this action is contained in this number nu, right? This length scale 1 over A is really not important, and I should be able to somehow hide that information because that's not essential. Okay? Okay, so let me explain how I can think of 1 over A as a quote-unquote gauge field on par with electromagnetic gauge field. So usually when we describe a crystal, we think of it as a lattice of points, right, in real space, the Bravais lattice that expresses the periodicity of the crystal. But there is another way, an equivalent dual way. We can think of a crystal in terms of intersections of crystal planes, right? Usually when we draw a crystal on a piece of paper, that's what we do. We draw a bunch of intersecting lines, and that's precisely this dual view of the crystal. And so mathematically, I may think of those planes as planes of constant phase in the following ways. I can let's say if you have a three-dimensional crystal, I will introduce three phase functions. So theta I, where I is 1, 2, 3, that depends on x and t, position and time. Okay, and so those crystal planes are solutions of the equation theta I is equal to 2 pi times an integer. Okay, so if I take a perfect crystal without any distortions, then theta I are just linear functions of positions. Position and the coefficients are simply the corresponding reciprocal lattice vectors, right? So you know that reciprocal lattice vectors define families of planes. Okay, and then the solutions of these equations for x will give you precisely the Bravais lattice vectors. Okay, and I can calculate the reciprocal lattice vectors from here just by taking gradients of those phase functions. Okay? Now, the important point is that this actually makes sense even if the crystal is distorted, right? If my planes of constant phase are actually no longer planes, some surfaces in real space. So I may still think of gradients of those phase functions as defining a local basis in the reciprocal space, basically giving local reciprocal lattice vectors, which are now fields that depend on x and may also depend on time. Okay? And it's going to be convenient to include a factor of 1 over 2 pi into the definition. So I'm going to think now of these fields EI mu, right, as defining a local basis of the reciprocal space in principle deformed crystal. Okay? I can also connect these quantities to kind of more traditional quantities used in elasticity theory. So, for example, you can calculate atomic displacements U in this way using those phase functions. Okay, so these fields E may be viewed as quote unquote elastic gauge fields in the sense that they, in addition to encoding the geometrical information about the local orientation of those crystal planes and the distance between them, these fields actually also encode some topological information, in particular the curl of those fields, or in a differential form language, dE. So determines the dislocation density in my crystal, right? So if I take a circulation of this field around the loop in a crystal, this tells me the number of dislocation lines piercing the loop. Okay? And also, if I integrate this around the whole sample with periodic boundary conditions along a particular direction, this is just going to give me the number of unit cells in the crystal. Okay? So these are not true gauge fields in the sense that for true electromagnetic gauge field, the gauge field itself really has no meaning. It's only the curl that has a meaning. Here, this field itself has a meaning. Again, it tells you the local orientation of the crystal planes and the distance between them, but it also carries a similar topological meaning to gauge fields, basically the density of defects and also the overall size of your sample in integer units, not just the number of unit cells. Well, so again, if I take just an undistorted crystal, undistorted one-dimensional crystal, we have the reciprocal lattice vector, just 2 pi over A, and so I can use this formula to calculate E, right? And so this just gives me 1 over A, okay? And so what I will do now is just a notational game. I will just replace 1 over A in this formula here by E. Okay, and I'm going to write my action in the following form. Okay, notice that I've added here a time component of this gauge field E that was not there to begin with. I will explain in a second what that means. But now what this looks like, so this looks like a topological term, right? It just involves a couple of gauge fields and a number in front. Okay, there is no metric, there are no length scales involved. So the time component that I have added by hand actually also expresses an important physical property of a metal. this expresses the fact that if I consider my 1D sample to have periodic boundary conditions, and I insert a flux quantum through the hole, okay, if I insert a flux quantum through the hole, this actually leads to overall change of momentum of this system by 2 pi times that number nu in units of 1 over A. Okay? So that's another property of a metal. And so I get this induced momentum by differentiating this action with respect to the time component of my translation or elastic gauge field E. And this is because the time component of this gauge field is simply velocity, right? And velocity couples to momentum in the action. Okay. Now, so another important property that I want to mention here is, so if you look at this action, it actually lacks gauge invariance, right? So it's problematic. It lacks gauge invariance. Namely, it lacks gauge invariance with respect to a large gauge transformation of my field A0. Okay, so by this, after I make this gauge transformation where beta is 1 over temperature, right? So then my action changes by this number, which is generally not an integer. Yes. Right. But why now it's always a single? Well, because so you see, this is not new, right? This is the momentum. This is the momentum that's induced by a flux, right? But it's related to nu, right? It has to be related to nu because the only parameter this action has is nu. Right? Okay, so the zeroth component of E is not just the one. Yeah, no. The zeroth component of E is the time derivative of that phase. It's a velocity. And so what this lack of gauge invariance implies is that, yeah.
So in the previous slide, you said that the time component of E is velocity. Can you elaborate a bit more on that part?
Well, so it's just the time derivative of that phase, right? And the phase, as I said, can be related to atomic displacements in this way. So that's why it's velocity.
But E is how we traverse in the momentum space.
So well, the spatial components of E, these are just the local reciprocal lattice vectors. But now I've also added a time component. And the time component is basically just the velocity, right? If I have a time-dependent distortion of the crystal, then this is the velocity that corresponds to that. Okay? I mean, don't worry if this makes you uncomfortable. This is natural because this is the first time you see it. You need to see it a few times before you become fully comfortable. Okay, so what this lack of gauge invariance implies is that this cannot really be the whole story, right? The whole action of your material cannot just contain this plus, E squared minus B squared, like it would be in an insulator. It must be, this implies that there must be additional gapless states, gapless modes, okay, that fix that lack of gauge invariance, okay? And that's another way to see that basically when I have a fractional nu, I must have a metal, okay? Or I can also have, of course, a broken translational symmetry, in which case the meaning of nu is changed. It becomes an integer because the reciprocal lattice vector is resized, okay? Or in a more exotic situation, but not in one dimension, you can have topological order. So this statement here is called, is an example of what's called the Lipschutz-Matisse theorem, okay? So which basically says that in this context, that if this parameter is fractional, I must have gapless states, okay? Or these other things. Okay, and so now let me show the following. now let me show that I can obtain the same result, namely the same action, from the other side, namely just looking at the low energy part of this dispersion. Okay, so suppose now, so I'm referring again to this to the Leichenger's theorem, right? So we've talked about the right-hand side of this statement. Now I'm going to talk about the left-hand side, okay? And I'm going to show that only thinking about the low energy electronic properties of my system, namely just knowing that I have two gapless modes, I can obtain the same result, okay, without referring to any properties of non-interacting electrons. Okay, so let's see how this works. So if I just look at this linearly dispersing left-handed and right-handed modes and forget about the whole dispersion, okay, then what you can notice is that these low energy states have actually an enlarged, or what I will call emergent symmetry. Okay, the symmetry here is, I will call this U1 left cross U1 right, and this corresponds to a separate conservation of the left-handed and the right-handed electrons, right? So if I just look at modes in the vicinity of the Fermi points, I have two independent branches of the right-handed and left-handed dispersion. I don't know that they are connected. Okay, so then these states have an enlarged emergent symmetry, and then if I take this symmetry literally, namely if I say that this is the true microscopic symmetry of my system, then I run into a problem, an anomaly. It's called an anomaly. And the problem is that this cannot actually be realized in a one-dimensional lattice, right? On a lattice, those left-handed and the right-handed modes are always connected like this, right? So this left-handed and right-handed chirality cannot be globally defined conserved quantum numbers. Okay, one always goes into another. Okay, so I have an anomaly. Now, but where this kind of system can exist, okay, and this is the standard description of this kind of anomalies, where this system can exist is on the surface of a higher dimensional topological insulator. Okay, so in this particular case, this can exist on the surface of a two-dimensional topological insulator, of a two-dimensional quantum spin hole insulator that has this pair of left-handed and right-handed modes as H states. Okay, so if I have a single chiral H state, that can exist on the surface of a two-dimensional quantum hole insulator, right? But if I have a pair, right-handed and left-handed, that can exist on the surface of a 2D quantum spin hole insulator. And the theory that describes that looks like this. So this is just two Chern-Simons terms with an integer coefficient, which are time reversed, right? And I've introduced two gauge fields, right-hand, a right and a left, that corresponds to the separate conservation of the right and left-handed electrons. Okay. And so now I can express those two gauge fields in the following way. I can express them in terms of an electromagnetic gauge field A, which couples symmetrically to the right and the left-handed electrons. It doesn't care about chirality. And then a chiral gauge field E, and I called it by the same letter as my translation gauge field because it's basically clear that this must be the same thing, right? And it's clear by just thinking about how translations act on those modes. Okay, and you will see that they act basically in this way, where this theta is precisely the phase function that I have introduced before. Yeah.
On the previous slide, why was it a U1 symmetry?
Well, so because you know, mathematically, I can express the symmetry as a separate phase rotation of the right-handed and the left-handed electrons, right? the usual charge conservation symmetry, I can express it mathematically as the fact that I can multiply every electron operator by a phase factor, right? But here the symmetry is higher. I can multiply the left-handed electrons and the right-handed electrons by their separate phase factors, and my Hamiltonian will still be invariant under that transformation because there is nothing coupling the left and the right. Okay. So I can write them in this way, and basically this makes clear that this E is just the translation gauge field. So it's a true U1 gauge field in this low energy situation when I have really exact conservation of the right-handed and the left-handed charge. The true symmetry, of course, is not U1 left cross U1 right, is U1 cross Z, where Z corresponds to translational symmetry, discrete translational symmetry. So then, but if I identify this E, this my translation gauge field, okay, well, and again, this argument makes it clear that I should identify this U1 gauge field here with my translation gauge field, okay? And then if I do that, so if I substitute this into here, right, I get this action in 2 dimensions. This is what's left. And if I integrate this in the presence of a one-dimensional boundary, which represents my physical one-dimensional metal, I get this. And this is precisely the previous action that I have obtained by just thinking about the microscopics of my system, how much charge I have per unit cell. Okay. So what I've done is, again, I've connected the left-hand side and the right-hand side of the statement of my Licensure theorem without referring to non-interacting electrons. Okay? This, of course, should not be viewed as a proof of Licensure theorem. Okay? This is just a nice, slick argument. But the nice thing about this is that this is true always. So in all the realizations of metals that we know of, in particular in topological semimetals, this always works. Okay? So basically all I need to know is the form of the low energy spectrum, the low energy modes, and this sort of argument, thinking about the symmetry, the emergent symmetry and the anomalies of the emergent symmetry, is going to give me the topological response. Right? So it's trivial here, of course, but it may be non-trivial in topological semimetals, for example. Okay, so again, the value of this argument is that this connects a microscopic property, which in this case is the number of electrons per unit cell, to a low energy property. So in this case, volume and momentum space enclosed by the Fermi points without referring to non-interacting electrons. Okay? And so this connection is topological, right? You start from emergent symmetry, the anomaly, and then higher dimensional topological insulator, which may, it's suggestive that this property is robust to interactions, right? Again, it's not really a proof of anything, but it's suggestive that why these properties are robust to aiding interactions or in general any perturbations. Okay. Okay. So as I said, this works always. Let me just look at time here. So this works always. So for example, I can generalize this to higher dimensional metals, right? So let's say I take a two-dimensional metal, so then the Fermi surface is a line in momentum space, right? I can parameterize this line by a parameter theta, and yeah, sorry, this is a poor notation. This is not related to the previous theta. This is just a coordinate in momentum space that parameterizes this line, okay? And so the difference here from the one-dimensional case is that, so in the one-dimensional case, the Fermi surface just consisted of two discrete points. Here it's a whole continuous line, right? But that's okay, and the trick here is to view this parameter theta as an extra dimension, okay? this two-dimensional Fermi liquid has the same emergent symmetry, and the emergent symmetry here is separate particle number conservation at every point on the Fermi surface. Okay, so if you've seen Fermi liquid theory, this is basically the basic assumption of the Fermi liquid theory, that you have the separate electron number conservation at every point on the Fermi surface. Okay, this emergent symmetry is again anomalous. If we take it seriously, if we say that this is a microscopic symmetry, it cannot actually be realized in any two-dimensional lattice model. Okay, but where it can be realized is again on the surface of a higher dimensional topological insulator. So in that case, topological insulator is in 2 + 1 + 1 + 1 = 5 space-time dimension. And the extra +1 is the dimension of that theta that parameterizes the Fermi surface. Okay? And there is also, in that case, an additional component to the gauge potential. There is also a gauge potential that lives on the Fermi surface in momentum space, and that's just the Berry connection, the gauge field in momentum space. Yes?
So when you said like that there's an emergent symmetry about separate particle numbers, like what are the physical implications of?
Well, it's basically the Fermi liquid theory. So Fermi liquid theory follows from that. The implication is that the properties of a metal are pretty much the same as the properties of non-interacting electron gas. Yeah, so the linearly, the heat capacity that depends linearly on temperature and so on. So again, I can write that 5 or 4 + 1 dimensional gauge field as a sum of the electromagnetic gauge field, which doesn't care where you are on the Fermi surface, and then of now 2 translation gauge fields, because I have a two-dimensional system, right? And the charges of those 2 translation gauge fields are just the components of the Fermi momentum on my Fermi line, on my Fermi surface. Okay? And if you plug that in here and integrate, so this is going to be the non-vanishing part, right? And again, so integrating this around the Fermi surface. Sorry, I'm skipping the details because otherwise I would never finish this talk. So this gives me this two-dimensional theory, okay? And this is precisely the Leichenger's theorem of a two-dimensional Fermi liquid. Okay, so this just expresses the fact again that I have charge nu per unit cell. Yes.
Just wondering, where are the two-dimensional notations?
Where the
So in your theory, there's Ex and Y corresponding to the X and Y components of your two-dimensional plane.
right,
And there's a notational symmetry.
right, right. Right. So the rotational symmetry, the rotations are not important here. So what's important here is translations. Rotations are important for some other, in some other cases, like for, let's say, for Dirac semimetals. So in that case, rotation gauge field, an analog of this for rotational symmetry enters. Okay? But here it's only translation that are important. I mean, I drew a symmetric Fermi surface, but the symmetry really doesn't matter. The rotational symmetry doesn't matter here.
But your action should preserve this.
Sorry?
But should your action preserve the even though you said
I mean, if there is a rotational symmetry, then I guess yes. But in this, for this property, it's not important. Again, this just expresses the fact that I have certain charge per unit cell. The rotation symmetry is not important there. Okay. Okay. So now let's move on. Let's see how this works in the case of topological semimetals. So let's take the simplest example again, a magnetic wile semimetal. Okay. So in this case, in the simplest situation, I have just two wile points. I can call them right-handed and left-handed again, where three-dimensional bands touch. Okay, and suppose the distance between those points is 2q. So the points are at momenta plus q and minus q on the z-axis. Okay, So, so as I mentioned, this may be thought of as an intermediate phase between a quantum anomalous Hall insulator with quantized Hall conductivity given by E squared over H per period, okay, per lattice period in the z direction, and an ordinary insulator where the Hall conductivity is 0, right? And its most important property is that it has a Hall conductivity that's basically proportional to this separation between the Weil points, right? Its Hall conductivity is equal to E squared over H times basically that distance divided by 2 pi. And I often use units where E and H bar are 0 or are 1, sorry. So in those units, it looks like this, okay? And so as I will argue, basically this is what replaces the Leitinger's theorem of a metal in this case, okay? Yeah.
Is B the lattice spacing?
It doesn't matter what B is, it's just some parameter, sorry. So this is going to be a magnetization, let's say, in a Weil, in this magnetic Weil semimetal. You can tune magnetization and go from an ordinary insulator to a quantum Hall insulator through this Weil semimetal phase. Okay?
So the bottom line is the insulator part, and then it goes
So
to
this here, this region is the ordinary insulator. Hall conductivity is 0. This is the quantum anomalous Hall insulator. Hall conductivity is quantized to E squared over H divided by D, where D is the lattice constant. And in between here, you have the Weil semimetal. Okay, so I can now use the same logic to derive this. Suppose I didn't know this, right? But I can use the logic that I explained previously. So if I just look at low energies, this again has a separate conservation, just like one-dimensional metal. It has separate conservation of the right-handed and the left-handed electrons. Okay? So therefore, it has the same enlarged emergent symmetry. So U1 left cross U1 right. Okay, this symmetry is anomalous. Again, if I take this symmetry as a true microscopic symmetry, I run into a problem. This cannot be realized in 3 dimensions. Okay, but it can be realized on the surface of a 4-dimensional topological insulator. In this case, it's 4-dimensional quantum spin Hall insulator. Okay, it's 4-dimensional again because it's 3 plus 1, the 3 physical plus 1 extra dimension. It's described by a 4-dimensional generalization of the Chern-Simons theory, right? So this is the Chern-Simons theory for a 4-dimensional quantum Hall effect with a 4-dimensional integer quantum Hall effect. And so I take 2 of them with a minus sign, right? These are 2-time reversed copies of a 4-dimensional quantum Hall insulator, and I write my A right and A left again as in terms of an electromagnetic gauge field which couples symmetrically, and a translation gauge field which couples antisymmetrically, and the charge is just the momentum of the corresponding point. Okay. Let me skip that, and this is what I get. Okay, so this is what I get for the theory that describes my 3-dimensional magnetic Weil semimetal, and what this expresses is precisely this. It expresses the Hall conductance per atomic plane, okay, which is given by lambda divided by 2 pi, where lambda is the ratio of the separation between the Weil points to the length of the reciprocal lattice vector in the z direction. Okay, and so this is the analog of my Leitinger parameter for metals. Okay, so basically, whenever that parameter lambda is not an integer, so whenever I have a non-integer Hall conductance per atomic plane, I cannot get an insulator. Okay. I must get a Weil semimetal, and the separation between the Weil points in this Weil semimetal is given by, basically, is determined by this parameter lambda. So this statement is the analog of the Licensure theorem for a metal, in which case the fractional filling, fractional number of electrons per unit cell, determines the size of your Fermi surface. Here, the fractional Hall conductance per atomic plane determines the separation between the Weil points. So it's exactly the same statement. While the normal Licensure parameter in this case is an integer, right? Because I have a bunch of filled bands and a bunch of empty bands. So that is trivial, right? But there is again an analog of the Licensure theorem that says that I still must have gapless modes. Now, so aside from that Hall conductivity, this has another important piece of information. So imagine I insert a magnetic flux tube in my magnetic flux quantum in my Weil semimetal. So this is going to be a line. Let's say this line runs along the z direction. Okay. So what this means basically is that this dA in here is equal to 2 pi. Right? So along that flux tube, I have a curl of my electromagnetic gauge field that's equal to 2 pi. So what this gives me is this action for, which now only exists on my flux tube, and this is nothing but the action that describes the Licensure theorem in a one-dimensional metal. Okay? With a Licensure parameter lambda. So basically what this tells me is that in magnetic field, on every flux tube carrying magnetic flux quantum, I must have, in my Weil semimetal, a one-dimensional metal discharge lambda per unit cell. Okay? So what this expresses is the following well-known property of Weil semimetals, that in magnetic field, the Landau level spectrum looks like this, right? So I have a bunch of Landau levels that just basically have a similar shape to the Weil dispersion, right? But there is a special Landau level that basically crosses the Fermi energy, the zero energy, at the location of the Weil points and connects them. Okay? So in the language of this action, this can be, it is described by this. Okay? And it's again, its Licensure volume is just given by the distance between the Weil points. Well, so this also works for this. Oops, this also works for. Sorry, something happened here. Yeah, sorry, for some reason it left the. Okay. Yeah, sorry about that. So this works in all cases. Okay, so I don't know if I have enough time really to go into details, but so for example, this same logic works in non-aligned semimetals. So in that case, it's completely non-obvious what the topological response is, right? So in this case, we have a pair of bands that touch along a line, right? And it's entirely non-obvious what the response is. But again, if you go through the same logic, emergent symmetry, anomaly, topological response, what you find, and let me skip the details because then I won't be able to go through the second half of the talk. Basically, what you find is that the topological response corresponding to that is a polarization. Okay? It's a polarization, electric polarization, whose magnitude is proportional to the area enclosed by the nodal line. Okay? It's basically a spontaneous polarization, spontaneous meaning that there are two signs that correspond. So you remember that the nodal line is protected by mirror symmetry, right? So this material really can't have an electric polarization because of the mirror symmetry. Okay, but a polarization is going to be induced by infinitesimal breaking of that mirror symmetry, right? And the sign corresponds to the sign of that mirror symmetry breaking. Okay. Well, again, if you are interested, we can talk later about this. Let me now go to the second part of the talk, which is going to be the transport properties, and I'll have to go through this quickly. So let me talk about only the transport properties in point node semimetals, and I'll specifically talk about, again, the simplest case of magnetic wire, but this is going to be generally applicable to all point node, not line node, topological semimetals. So again, as we discussed, in this case, we have an emergent low energy symmetry, right, which corresponds to separate conservation of the left-handed and the right-handed electrons. And I can regroup those in this way. I can talk about the separate conservation of the total charge, which is the sum of the left-handed and the right-handed, and the chiral charge, which is the difference, right? So in this case, if both of those were really strictly conserved, their transport would be described by two independent diffusion equations, diffusion equation for the electrical charge and diffusion equation for the chiral charge, right? And I've added here some relaxation term for the chiral charge just to account for the fact that in reality it's not strictly conserved. There is always some impurity scattering that's going to still connect the left-handed and the right-handed. Okay? But basically what you can say is that we get unusual transport properties in this case if this chiral charge relaxation time is much longer than the momentum relaxation time. Okay? If this is not the case, then basically the transport properties are no different from an ordinary metal. Okay? So I'm going to assume that this is the case. Okay? And again, as we discussed before, this symmetry is not really a symmetry, it's anomalous. Okay? So another way in which this anomalousness manifests is in the fact that this conservation of the chiral charge is violated in the presence of electric and magnetic fields. Okay? So as we discussed, there is this, in the presence of magnetic field, I have this lowest Landau level, which connects the left-handed and the right-handed electrons, right? And then if I, in addition, add an electric field, this is going to lead to a drift in the presence of electric field. And this drift basically looks like the chiral charge non-conservation. Looks like pumping of electrons from right-handed to left-handed, let's say, or vice versa. Okay? Now, a consequence of this is that if I actually derive diffusion equations for this magnetic wild metal, this is what I find, right? So I get my usual diffusion terms plus this relaxation, and I've added here an external potential for both the electric and the chiral charge, just as a mathematical device, okay? So the sum then of n plus density of states times V, you can think of this as the electrochemical potential, okay? And the same thing for the chiral charge. But so this anomaly manifests in the fact that in addition to those standard terms, I have these terms. They are proportional to the first spatial derivative, okay, and to the magnetic field, okay. And so basically what those first derivative terms express is the ballistic transport in this one-dimensional metal that's induced on every magnetic flux line, okay. And so there is a new transport coefficient here, gamma, that's basically just proportional to the magnetic field. Okay? And the fact that, you know, this effect has topological origin is manifest in the fact that this coefficient is not really renormalized by disorder. It's still magnetic field and the density of states. Okay? Now, so you may think that, you know, these new terms may be not important because they come from just a single Landau level, right? And if I have finite density of states, let's say if I have a finite Fermi energy or just density of states that's going to be generally induced by disorder, that this single mode is not going to matter in comparison to all the other contributions, the usual contributions to transport. But that's not the case, and the reason here is that you see that the usual diffusion terms are related to second derivatives, while these new terms involve first derivative, right? And the first derivative will always dominate second derivative on long enough length scales, okay? No matter how small the coefficient. So basically, first derivative will always dominate at long length scales until we reach the chiral charge diffusion length, which is basically related to that time that I assume to be long, okay? In which case, basically, the two nodes will be mixed very strongly, and then all of those effects, unusual effects, go away, okay? So basically, what I will show, what this presence of these terms leads to is propagating modes and quasi-ballistic conductance, which exists in a three-dimensional metal, which is very unusual. Okay? Basically, one-dimensional like physics in a three-dimensional metal. Okay, so in order to see this, the easiest thing to do is just to diagonalize this. Well, I can Fourier transform basically these equations and find the eigenmodes. Yes.
So the gamma terms, are they similar to like Christoffel symbols in gravity, like where we add them as a correction to because there's curvature of space?
Well, no, not really. So again, this is just ballistic. This is just ballistic conductance on that 1D metal. Yeah, this is not related to curvature. It's just the same letter. Yeah. So if I do that, so these are the two eigenmodes that I find. There are two equations, right? So I have two eigenmodes, the frequencies as a function of the wave vector, and so the most important thing here is this square root, right? So the first two terms, that's just the usual diffusion modes plus relaxation, okay? And so if I look at the square root, you see that, well, if Q is very small, so on very long length scales, this doesn't really matter, and so I just get the usual diffusion modes, basically diffusion of ordinary charge, omega equals dq squared, and diffusion with relaxation of the chiral charge, okay? So this corresponds to longest length scales when I have exceeded the chiral charge diffusion length, okay? But then if Q is greater than this, right, then you see that this square root gives me an I, right, which cancels an I on the left here, and what I get is basically a propagating mode, a linearly dispersing propagating mode, where the velocity is given by this parameter gamma. So velocity is proportional to the magnetic field. There is also a diffusive damping, but as long as Q is not too large, namely the length scale is not too short, this is going to dominate this, and I get a weakly damped propagating mode. Okay? And so specifically, this mode is weakly damped as long as Q is less than this ratio of gamma over D, which defines a new length scale for me that depends on the magnetic field. Okay? And so basically, to summarize this, so this linearly dispersing propagating mode exists as long as Q is in this interval, okay, between 1 over L star, where L star is related to the chiral charge diffusion length in this way. So it's LC squared divided by this new magnetic field dependent length, LA, and 1 over LA, okay? And so the existence of this propagating mode in the diffusive transport regime is really even in weak magnetic fields, this is the main qualitatively new feature of point node topological semimetals. That's behind all of their unusual transport properties. Okay, so I need to wrap up quickly. So basically what the observable phenomena that this leads to is the following. So one of them is a scale-dependent conductance. And so basically when your sample size is in between those two length scales, the conductance depends on the length scale just as in a one-dimensional ballistic metal. This just basically counts the number of these one-dimensional modes that are induced by the magnetic field. And the conductance per mode is just E squared over H. Okay? So this is not like the usual ohmic conductance in a three-dimensional metal would behave. Right? So it's this quasi-ballistic conductance. Another observable manifestation is what's called chiral magnetic effect that leads to a negative longitudinal magnetoresistance. So basically, what this form of the diffusion equation for the electric charge leads to is this additional contribution to current that's proportional to the magnetic field and the chiral chemical potential. And so what this leads to is negative longitudinal magnetoresistance that's very large. It's basically, its magnitude is proportional to the ratio of those length scales, LC and LA, where LC is the chiral charge diffusion length. And so this can be very large, several 100%. And this has already been observed in some materials like cadmium arsenide and sodium 3-bismuth. Okay, so again, I don't really have time to talk about this in detail, but yet another observable manifestation of this can be seen in the optical conductivity. Basically, in the optical conductivity, the fact that you get these one-dimensional modes in magnetic field, what this leads to is an extra peak in the optical conductivity in addition to the usual Drude peak, whose width is given by 1 over tau c rather than the usual 1 over tau. And if 1 over tau c is much smaller than 1 over tau, what you get basically is a narrow peak that grows on top of the usual Drude peak once you turn on a magnetic field. Okay, so let me, and this seems to have been observed. So let me stop here, and yeah, I can take any questions.
Time for a quick question.
Right. Well, I mean, it's not obvious that it's going to be larger. Yes, that's so a good topological semimetal would be defined by tau c being much larger than tau, right? But so so since these points are separated in momentum space, right? You would expect that if the impurity potential is smooth, right, then it would not scatter. Would not scatter strongly between those 2 points. So then you can expect tau c to be much larger. But in principle, it doesn't have to, unfortunately.
I have a second short question. So the spontaneous electric polarization, does that only apply to the light semiconductor, or does it also happen for point?
Well, no. So it can happen. Let's say in topological insulators, right? You can get an electric polarization of a half because of the edge states, right? But as far as semimetals are concerned, yeah, this is a property of a non-aligned semimetal.
Yeah, that is a really quick question. So you're talking about the Ledinger theorem for 2 plus 1D theory, and I'm a little confused. So I know you have a 2 plus 1D theory and it couples to theta, so you have an additional space-time dimension, but I'm missing one.
Well, this is just time. I was talking about the space-time.
So you have a 2 plus 1D and you have theta, so this is 4.
4, yeah. 4 plus, yeah, the plus 1, that's just the time. So it's 4.
Should be 4D.
Yeah. It's four space dimensions, but because the theory involves time as well, then it's 5 space-time dimensions.
Okay, maybe I'm still not clear on it, but I can ask you.
Sure.